The Gulf of Corinth is an active extensional marine sedimentary basin thought to have started deforming during the late Miocene, Pleistocene epoch. The dimensions of the Gulf of Corinth are approximately 105 kilometers long and 30 kilometers wide, with a basement depth of 3 kilometers at its center. This half-graben basin is formed by a N100 E-oriented rift which separates the Peloponnese peninsula from the continental mainland of Greece. Currently the Gulf's rift is opening at rate of 10 to 15 millimeters per year. With respect to the Eurasia Plate, the basin is bounded by the Peloponnese highlands to the south and the westward-moving Anatolian Fault to the north. Major and minor fault plains make up the north and south margins, and its north-south extension is due to activity along AEW to NW E-oriented coastal southern margin. The basin's active and inactive faults create associated syn-rift sediment fill. These aspects provide a unique opportunity for scientists to study the tectonic and stratigraphic development of a rift. While further understanding how a basin is actually made, it is postulated that crustal extension is related to a combination of factors: westward movement of the North Anatolian Fault, gravitational collapse of the thickened Hellenide orogenic crust, subduction, and slab rollback of the African plate at the Hellenic Trench. As Africa subducts beneath the Aegean plate, the slab essentially pulls the overriding plate with it, inducing extension. Rifting occurs as the plate stretches, weakening the thickened crust, causing its collapse upon itself, creating the basin. Fault activity: Western Gulf of Corinth, Aegean to Akrata. The North and South Eratini faults offshore the Western Gulf are 15 kilometers in length, overlapping completely, uplifting a notable basement host. The south-dipping West Channel Fault controls the western draining axial channel, which widens eastward as the northern margin becomes controlled by the south-dipping East Channel Fault. The East and West Eleki and Aegean faults control the coastline on the southern margin. The Akrata Fault may be part of the East Eleki Fault, a group of south coast landward inactive faults. Mamorsia, Piegarchi to Calabrita, are thought to have contributed to extension in an earlier phase of the rift's evolution. Central Gulf of Corinth, Akrata to Xylocastro. The northward-dipping 30 to 40 kilometers Corinth Fault lies along the southern margin boundary between Akrata and Xylocastro. This fault, once thought to be just a single fault, is supported as being split into two segments. The western segment is the Derveni Fault and the eastern segment is the Lycoporia Fault. The northern margin boundary is the eastern extension of the East Channel Fault and the south dipping Western Antikythera Fault. In adjunct with these active faults there are a few inactive faults, such as the onshore Xylocastro, presently located in the footwall of the offshore Lycoporia Fault. Eastern Gulf of Corinth, Xylocastro to Perachora Peninsula. The northern basin margin is defined by minor fault segments such as the southward-dipping Eastern Antikythera Fault. Several inactive buried faults, N and S, Corinth, produce localized subsidence. The east and southern margin is controlled by two 12-kilometer-long northwestward-dipping Perachora faults and the northward-dipping Xylocastro Fault. Alkyrenides Gulf. Significant faults are the offshore north-dipping West and East Alkyrenides Fault and the onshore north-dipping Pisia and Skinos faults. Both Pisia and Skinos faults mentioned are major structures controlling the topography. The West and East Alkyonides are not connected at the surface and they seem to overlap. These faults control the uplifted Strava Graben and uplifted Alkyrenides Islands. On the northern shore, south-dipping faults are much less notable. In 1981, a sequence of earthquakes reactivated the Carpelli Fault, which has since then had low and infrequent slip rates. Stratigraphy, sedimentation, deposition in the Gulf of Corinth occurred in at least two phases, separated by a widespread unconformity. Deposition before 400 Ca marks the first phase, likely open to the east, was filled with continental and shallow water deposits with subsidence rates slightly exceeding sedimentation rates. Average uplift rates during the late Quaternary are estimated between 1 to 1.5 mm per year on the southern margin, increasing during the Holocene at 1.3 to 2.2 mm per year. The high uplift rates expose many marine terraces and other continental to marine deposits. Infilling of the basin began in the Pliocene, depositing continental and shallow water lacustrine facies followed by marine sediments in the Middle Pliocene. This phase can be called Proto-Gulf of Corinth, as it was a different size and fill than the present-day basin and had two different 20 to 50 kilometers wide depot centers. These depot centers, controlled by north and south dipping faults, crop out near the south margin on the Peloponnese inland. Subsidence is linked to the fault systems bordering the depot centers, which have quickly developed in the basin's relatively short 1 to 2 ma existence. Sedimentation can be subdivided into transgressive and regressive trends. The lower transgressive sediments are based with alluvial fanglomerates followed by alluvial plain conglomerate rocks. On top of this is seasonally flooded forest deposits indicated by organic rich mudstones containing leaves of Acer cf. Viminalis and Platanus s. Tabular-bodied transgressive beach deposits are interbedded with fine-grained sediments and lignite, alluding to freshwater lacustrine-like environment. Animal life fossilized in lacustrine marls consist of fewer Oligocene ostracods and mollusks, indicative of fresher shallow brackish water, suggesting the basin had very shallow waters even in its most open condition. Overlying these are regressive beach-type deposits, displaying large-scale faucets and a coarsening upward sequence. Passing from open water, the facies change to near-shore and alluvial deposits. A 1,000 meters basin-wide fanglomeratic unit overlays these deposits. The second sedimentary phase is marked by a dramatic increase in subsidence, unmatched by sedimentation. This phase has a complex history and is composed of deep-sea deposits and Gilbert-type deltas, sitting unconformably on the fanglomeratic unit. A fault group with a displacement of approximately 600 meters created the basis for the deepwater Gilbert-type deposits. These older Everestini Gilbert-type delta deposits were then uplifted to 800 to 600 meters above sea level, and the younger Ilias Gilbert-type delta formed. This fan delta is approximately 400 to 300 meters above sea level, putting the Everestini deposits 1,200 to 600 meters above sea level. Present-day Gilbert-type deltas form on the basin margin as the result of transfer faults perpendicular to the main extension. The present Gulf of Corinth delta deposits crop out along the rim, supplying turbidite deposits, which are the basin's current main fill. Earthquakes. Under the North Peloponnese, there is a 5.5 to 10 km well-defined seismogenic zone that deepens to 12 km under the northern shore of the Gulf. This is responsible for an immense number of earthquakes in the region. For instance, in the summer of 1993, 232 earthquakes were recorded. Due to such active seismicity, many earthquakes activate new fault planes. It is hypothesized that extensional slip on EW striking 20 degrees to 40 degrees north dipping planes are caused by earthquakes beneath the northern shore. However, In the Aegean area, fault plains like the Helike Fault have much steeper dips of 55 degrees to 70 degrees that can be observed. This difference leaves the connection between outcropping faults and the seismogenic zone open for debate. Other hypotheses include steeply dipping faults but at a low angle seismically active detachment, or they undergo a progressive down-dip curvature and merge into low-angle detachments.